So let's talk about normal modes. One of your homework problems has the calculate the normal modes of oscillation of something, right? I think is a plate that can go up and down like that. And I don't remember if there's another one that has that too, the normal modes, how to calculate them. The one with the springs? All right, so what are normal modes? What do you understand as normal modes? Can you, sorry.
That has particular frequency.
So it is an oscillation and it has a particular frequency, right? But what else are those normal modes? So I think this is really important. So I want to double check that everybody has it. What else do you guys know about the normal modes? Shalini, looks like you want to tell us.
Is it, I don't know whether it's right, but is it true that it's always mostly associated with vibration motion?
So you have vibration motion. So these normal modes, the way to see them is that these normal modes are your oscillation coordinates. So let's say you had a plate. You calculate the normal modes. The normal modes, however many oscillations you can have, let's say you can have 3. Those normal modes, the oscillations, every type of oscillation can be now talked about as a combination of normal mode A, B, and C. Does that make sense? So if you have a normal mode, and this normal mode is this one, and then you have another normal mode that is this one, with those two, and then there's another one that is this one, right? Let's say those are the ones that you have. With those 3, now you can build every oscillation and describe it as a linear combination of the 3 modes. So it's kind of like a vector in a sense. The vector of position, right? The vector of position is given by X, Y, and Z. This is the coordinate of the motion. So for instance, here, this is a mode of vibration. So this is for graphene. And this is a mode of vibration. In graphene, all of the atoms are carbon, but this carbon and this carbon are not equivalent to each other. One is white and has these 3 neighbors that are black. And the thing that is not equivalent is that this one is joined in this direction versus this one that is joined in this direction. So you have 3 neighbors. The white one has 3 neighbors in this direction, 1 in that direction, whereas the black one has 2 neighbors in this direction and 1 in that direction. So they're not identical, they're similar, but not identical. So you have this mode of vibration where these 2 guys are going like this to each other. And then you can have this other mode of vibration where they're going like this, right? So this is not the only motions that they can do. If you grab a graphene lattice and you hit it in a random direction, you're going to excite this one and this one. Does that make sense? So this mode and this mode, they're not the only 2 motions that they have. You could actually do something like this. Does that make sense? Yes? No? I lost you? All right, and then you have other normal modes, like this is a normal mode right here. This one is quite interesting. This guy right here is that there all of those atoms are moving together, right? And if this guy is squished together, what happens to the atoms on this one, right? And this one. Those are squished together, the other one looks like they're breathing out. So if you go to my office, you'll see that there's a picture of this particular mode up there with pretty colors and everything in my door. What it is that you have a stretching and a compressing. And if you look at it, there's no way for this combined with this to build this one. So that's why this is a different mode than this two. Are those modes unique? No, you can have different modes all the time, different representations. But there's only as many modes as vibrations that you can have. Okay?
So if you're given a system and we are asked to find the normal modes, then we can assess the all possible motions and see which one are existent elements. And then we can solve for that.
So if I give you a system, right? All right, so this is kind of like what we were talking about in office hours on Wednesday. Let me go back to setting it up. Let's say that you had some spring right here, a mass 1. Then you had connected to another spring, this is mass 2. And then this is in mobile walls, right? Right there. So this is mass 1, this is mass 2. Let's assume they're both mass m for simplicity. We assume that this spring K and K are the same constant. And then you have the kappa spread. So I don't remember if we did this one in particular, I don't think so, in class, but we saw something with the springs. Maybe it was a pendulum?
Yeah, it was a
Double pendulum, right? But this is exactly the same thing now. The one that you have has 3 masses in the homework. But now the question becomes, what are the, once you're solving for this, I think the motion that I'm asking, what are the normal modes that you get? And the way to solve this, let me make sure I have those previous notes. Where am I? What you want to do well, there's different ways to solve it, right? What you might want to do is solve for the matrix, dynamical matrix of the system. And that's what we did in that class. And that's the method that I was hoping you would do for this. Now, well, I'm not finding my notes right away. Pendulum, pendulum. Double pendulum. Oh, here we go. Yeah, so I gave you the linear triatomic molecule, right? And I also gave you the double pendulum. And then in the pendulum case, you have to solve for, and you get this matrix right here is equal to this matrix. So this matrix, this is a matrix right here. And this is basically a vector, right? And this is a vector. So in this case, this was a rotation or an angle, and the rate of change of the angle can be described as that, the acceleration of that can be described as with this matrix of the original line. So this would be like if you have x1, x2, and x3, right? So there's an x double dot and can be described as you will have x1, x2, x3 in the matrix. So now the question becomes, how do I describe those normal modes? And if we were looking at this guy, right? You can find the eigenvectors, and then you may see that there's something that looks like this, and another motion that looks like this. Right? So those two are your coordinates. You can call this one coordinate 1, and this one coordinate 2. And those are your normal modes are going to be related to those coordinates. So you would have this normal mode, right? The two particles, masses moving back and forth like this, and then you'll have this normal mode if you only had 2. And if you have 3, you're combining 3 different normal modes and so forth. And you're finding those eigenvectors. So finding those eigenmodes, the frequency of those matrices is what gives you the eigenvalues gives you the frequencies. The eigenvectors gives you the modes, where is it this way or this way. And each of them is associated with one of the vectors in that matrix. So the one that you have is a matrix. You can build it because it's going to have 3 things in it like that. And once you build it, you can find what the eigenvectors is and all of the cool things about it. So hope that helps. If you have questions about it, you can ask me right now with everybody here so we can discuss this.
So I have a doubt in the first question.
Mhm.
That we discussed that we have a rotational kind of restrictive rotational kind of motion around the z-axis, right? How can we represent the potential of that? And I had a trouble in writing that particular Lagrange because while rotating, the springs will be extended in a different manner. Like it won't be like the normal vibrations of a spring.
Okay, so maybe this is why I want to see your setup, to see what you're thinking. Let me do this one here. So this is what I was thinking for this problem. You have a plate right here. And one is A, one is B, or 2A and 2B, I forget. And then this plate is connected in a way that this is the center of mass, right? And there's this axis going in this direction. Let's call this one C. There's this axis and there's this axis. So we can call this one X and this one Y. Okay. So now this is where maybe we're talking about different things. If you do this setup like this, there's something connected here. There's something connected here. So there's a roof kind of thing over here. And then they're like that. All right, so we see that there's this one where everything comes down and up. And that one hits you with the center of mass. Right? Then you can look at it this way. Let's say that now you had C right here and Y here. Okay. So now let me think about this one for a millisecond. Then basically This is one normal move. There's an angle right here, right? So that's this rotation like this. Your center of mass is not going to move. So your center of mass is still here, right? And you have the angle with respect to the x-axis like this.
Yeah.
So you can describe that one. Then you can describe the one that is the opposite, where we would have y, c, and it's this one. And then the last one is this one, like that. Does that help?
Yeah. And the normal height.
Sorry, I missed that.
The second one is exactly like this one, except it would be x. Right? So there's an x and c. So if you call this one 1, you can call the one that's going to here 2. And it's going to go oscillating to this one. And then the third one is, if you look from the top, it's oscillating with respect to the z-axis. So those are the 4 modes that you have to consider. In the thing I put 3, because I actually hadn't thought about the rotation until you guys brought it up on Wednesday. So this rotation like that.
I'm confused about how to give the potential energy term of the rotation around the z-axis.
All right. So do you have potential energy from rotation?
Because the springs will be elongated a bit, right? So,
Exactly.
yeah, because of that.
Right. So do you have, the first thing is this. You have the kinetic energy terms, right? And you're gonna have 1/2, whatever the mass of the thing times its velocity, right? Then let's call this one, I don't wanna give you ideas, but let's call this one theta. What do I have here then? In this direction, I don't know if I want to call it IX, maybe you want to call it I1, right? And what's next?
I see. Yes.
And then I have the other rotation that goes with the Y, right? Around the Y axis, right? And then I have to take this into account. So you have 2 springs that get stretched. In this one, right? This spring and this spring gets stretched. This and this gets compressed. And that's your potential energy. Now in the rotational one, if we go with rotation around the z-axis, in this direction, let's call this one psi, right? Then you do the same thing, and now we have to figure out whether there's a potential energy from the rotation. And if it's rotating just a minimal amount, this one gets displaced a little bit, this one gets displaced. Yeah. So then you have to add a line for your potential energy for each of those springs. But that's it, right? That's your potential energy.
Yeah.
So you have the mg.
We have to consider gravitation.
I don't know. Did I ask you guys?
I don't know.
I don't think so. Yeah.
Yeah.
But you do have to consider how much the spring is getting stretched. So that's the other thing to
Can we
consider there.
approximate, suppose spring is like this, can we approximate if that it will be exactly something like this, or it's something like this?
Exactly. So it's a small displacement. So if this thing measures 1, right, and this one measures 2, so the direction x is 1, the direction y is 2, let's assume that. Then this, you can assume that is 0.01. or 0.02, something like that. Very small, and that's it. Don't go too complicated. I mean, it could get really messy if you start trying to figure out everything else about it. Okay. Anything else about the homework? So we were talking about precession in the previous class. So let's compare this to how the Earth is spinning. So if we look at the Earth, here's the sun. Here's the orbit of the Earth. Let's assume something like this. Here's the Earth, not to scale. And this is the position of the Earth as it's orbiting. One of the things that happens is that the Earth has a particular tilt right here. So there's an angle here. And this angle is 23.5 degrees. The Earth is spinning with that angle theta, right? So it's spinning like this. There's the plane where it's orbiting. This red one is supposed to be the plane where the Earth orbits the sun. And then there's an angle. There's that theta, which would be exactly perpendicular to the plane. And we have that angle to account for there. If we look at it, so here's the same angle everywhere right here. So now, the rotation of the Earth in that direction, we can call that one psi. And we know that this psi is one rotation. The rate of rotation is one rotation a day. So that's the spin of the Earth. So those are the Euler angles for the rotation, the spin of the Earth. So we know that the Earth is going to bulge at the equator. That's why, because it's spinning, it gets squished like this. So it's bulging at the equator. And it's not a sphere, but it's a symmetric top. You also have that the moon and the sun exert a torque on the Earth, and that produces a precession of the Earth that is, so how can I draw that? So let me make, so here's my angle theta right there, right? With respect to that. And then we're gonna have, so the Earth is spinning like that on this axis, right? With this side. But you also have that there's another spin going here in this direction. Sorry, it's probably the opposite direction. like this. And this one is that spin. So psi is with respect to that axis. The one around theta, that's the spin of the Earth. And this one is the precession of the Earth, and it's the one that goes with respect to this axis. So the sun, because this is no longer a perfect sphere, but it has symmetric top, the Earth, the sun and the moon have a torque on it, and that's what causes this precession. So this precession, we can see it. You can see it because it tells you where the North Pole is. The North Pole and I forget the name of it. There's a star. Sorry? The pole star, yeah. So there's a star, and it can tell you what day it is or where you are in the calendar, because that one makes a circle like this around us. So you guys heard about this, right? Like if you look at a time delay, you can see that the sky is rotating like that. Well, it's not the sky rotating like that. It's this precession angle that we have. The sky doesn't rotate like that. Don't tell Kyrie Irving, he's gonna be confused about this. You guys know about Kyrie Irving? NBA player, flat earther, anti-vaxxer, went to Duke University. So the pole star is the one that is pointing the circle that it makes. And that's why we call it the pole star, is because it tells you how this precession is happening. And this precession is the opposite direction of the spin. So the spin of the Earth goes in one direction and this precession is in the other direction. So that's, it's called a retrograde. So there's a really good book by Han and Fitch, where they calculate the precession of the Earth due to the moon and sun with the same techniques that we're using in this section of from the book. But it's actually really complicated to calculate it. And really long calculation, similar to the other ones that we were doing, on how this gravitational forces from the moon and the sun provide this precession that we see, this retrograde. But we can do another analysis. And try to get it. And actually, this is from, it's called the astrology analysis. And I got this from a website, but I thought it was pretty cool. So you guys don't believe in astrology, right? No? What sign are you? What sign are you? Sign. I'm checking whether you believe in astrology. You don't know what sign you are?
Oh,
Katie, what sign are you?
Virgo.
You're Virgo? I'm Virgo too.
maybe I'm correcting. I don't know English grammar.
So were you born in August, in November?
Mid 16 July.
That,
It's called
yeah, that might make you a Cancer. So yeah, now you have to figure out who do you don't hang about, because if you're Cancer and you're, that's what astrology tells you. All right, so just to finish this up, this is what it looks like in December 22nd. This is what it looks like in September 21st, right? June 23rd. This is when and this is March 21st. when the stations change. That's where the Earth is. So I think I'm behind because I was supposed to do this in September.
And the predict anything on this thing, like they predict anything or.
Oh yeah, it's nonsense. It's just somebody that, yeah. But maybe somebody believes on it. I don't want to burst the bubble. So if you look up your daily horoscope, sorry, maybe you just add this and your horoscope today. So this is the analysis that they did. So Jesus was born in the age of Pisces. So if Jesus was into astrology, he would be looking at his daily horoscope. But now the scholars have been looking at it and they think that that's not the date of his birth. Whatever we're told is the birth of Jesus Christ is not correct, because they think that he behaves like a Capricorn, not a Pisces. So what that means, what sign you are, is what patch of the sky was the sun in during the first day of spring. So where did the sun look to be during this day? That's what your sign is telling us. And then the sky is broken up into the different sections, right? So Virgos are born in this particular month because it looks like where the sun was at that particular point, and then they're going through the different constellations. So as the Earth precesses, whatever event was happening is changing. And you have that the stars change. So whatever happened in 1970 that looked like during March 21st is not the same as in 2000 years ago or 2021 years ago, and so forth. So this changes because of the precession. And you have a different backdrop of stars as a result at a particular day. So the stars are not aligning the same way when you were born as when I was born. Even if we had the same date of birth, it's not the same year, so it's not the same stars that were shining upon us. So that's why the horoscope might be right, correct? No? Then, Jesus was born in the age of Pisces, and that's why so Pisces is the fish. And then right now we're in the age of Aquarius. So if you look at the houses of the zodiac, in around 2000 years, we traveled. So if you look at the order of the houses, we have traveled through all of them in around 2000 years, and we're one behind where Jesus was. So we're in Aquarius, and then there's Pisces. So this took 2000 years. So we did the whole, almost the whole circle. So we traveled backwards, sorry, we traveled backwards one by this age, right? So if we want to go to 12 houses, that would mean that we have to do 2000 times 12, which is 24,000 years. It's actually, so if you think about it like this, the precision is actually given by 25,700 years. So if you look at the astrologers, how much the sky has moved, If you wanted to go backwards the whole time, that would give us the precession that we're looking at. And the reality is that this 24,000 is for the zodiac, 25,700 years would be the real precession. Other things that are interesting, not zodiac things, but real things, is the angle here changes. It goes between 22.1 and 24.5. And the period of this is 41,000 years. So this angle changes with a period of 41,000 years. These changes are because of the planets giving us extra forces like Jupiter, Mars, Venus. And the eccentricity of the orbit gives us another period here of 105,000 years. So the orbit is not a perfect circle, it's eccentric, it's an ellipse. So that also gives you two periods that you're dealing here with. And if you have two frequencies, sine of two frequencies, right, going like that, you can see beats on it and it changes significantly. Questions? So now we're going to cover another topic. The formal ball bodies. How many of you have a cat? Just you? You guys don't like cats? You have a cat? All right, take your cat. No, don't take your cat. Grab a cat, flip it upside down, get up on here, let it go. What do the cats do? They rotate themselves really cool, right? Don't do that with the dog. Dogs are not gonna land on their feet. So why does that happen? How come he can twist his body and land on his feet without pushing against anything? Like basically, if somebody grabs you and throws you like this, could you flip yourself? How come a cat can do it? I always thought that that was interesting, that a cat can flip themselves like that. And actually, the flipping is what I think is interesting because they don't push against anything, right? They're just free falling and they're able to push themselves. So how do they do it? Do they have angular momentum inside of them that they can spring out to rotate themselves, or how do they do it? No. So they actually have zero angular momentum, but they're twisting themselves. So this is what I think now that you guys know all of this physics, right? You start thinking about things like that, like how does a cat land on their feet? What is it that they rotate against? They actually have if they were a rigid body, then you require angular momentum. But the cat is not rigid. The cat is not rigid. They are able to twist themselves. They deform themselves and they are reorienting themselves without needing angular momentum for this. So actually, this is really nice mathematics that we're going to be describing in the following. And there's this very famous physicist who came out with this paper. And are you guys familiar with this name, Frank Wilczek? You know who I'm talking about?
Yeah.
What did he do?
It's not working. It's again, I think he worked with David Gross.
And what did he get?
Nobel.
What year?
Oh, 2004.
Yeah, 2004. So he's a high energy theorist that got the Nobel Prize in 2004 on quark interactions. That's what he got the Nobel Prize for. But actually some of this on the lecture is based on this paper. And this was developed to understand how a microorganism swims. So this happened in 1989, this paper. So it's current research, right? Not very current, maybe as old as you guys research. People didn't understand how things could move when they were so tiny. So the first thing we have to do, let's look at the kinematics. So the first thing I need is to describe a configuration space of a deformable body. So the configuration space is the space of all the shapes with some orientation for a body. Let's say we had a deformable object. This is one of the possible shapes. This is another possible shape. And this is another possible shape. So these are possible shapes for the deformable body. So if we look at C, this configuration space, this configuration space wouldn't have translation because translations don't really matter in this, right? What we do have is that they should have a center of mass and that the center of mass should be at the same point in those deformable bodies. And the next thing is that the configuration space is this same deformable body can be deformed into these three things. The center of mass is at the same point in space. And now we have that the configuration space C is all of the possible orientations and deformations that we can have. So what that means is the rotations belong to this C. Rotation is a change in the orientation, right? You're simply rotating the shape. So all of the rotations, like for instance, if you put this guy upside down, that's just a rotation. That rotation motion that you did is part of this configuration space. So now we can have another space. So this is again this fancy C, curly C, and I can make a shape space. And this C with a tilde on top is already inside of the big C. This is gonna include all the rotations. So you keep the same shape. And that's a subset of C, right? And any of the configurations that are in big C are also in C tilde. And sorry, any one that is in C tilde is also in C. And anybody in C that is a configuration in C that is related to another configuration by just a rotation is in this shape space. So they kept their shape. Two objects have the same shape. And they're related by a rotation. You change the orientation of something, they would be described by this guy. So another way to consider this is that the way to mathematically define it we would have that C tilde is equal to C divided by S of 3. Question so far? No? All right. So we can describe this better by saying that a body consists of n masses. These are point objects, okay? The masses. Each of them is located at some position Ri. C is the space of all possible configurations Ri. We then pick some Ri tilde and this is a representative Ri with a particular orientation. So it doesn't matter which one you choose. You choose that one, and now you set that one as your coordinate. Just pick one, and that's now your coordinate. So if you need coordinates, you just choose a few of them. Now you have your 3 coordinates, or however many you need to describe what you're doing. Of this space C. So now for each Ri that belongs to the C, we always have a rotation matrix R that belongs to the SO3 group, so that you have that Ri is equal to this rotation Ri tilde. All right, so that's where I want to finish. This is for any continuous bodies. The dimension of C or C tilde, depending on the body that you have, doesn't have to be 3 dimensions. It could have a lot of dimensions. And you can see here, this would be kind of like the deformable bodies that we're considering, right? So they could have a lot of different orientations. All right, so we'll continue from there. I do have office hours today. If you have questions over Zoom, so let me know